All right. So now that we've talked about Ohm's law and how to combine resistors in series and parallel, we're going to talk about some circuit analysis rules that can be used to analyze any circuit, no matter how complicated it is. So we're not really going to analyze too complicated of circuits today, but we're going to introduce the analysis rules that will allow us to do so in the future. So these are going to be known as Kirchhoff's rules of circuit analysis, and there are two of them. We have a rule for voltages, which we will call the loop rule, and that relates voltage drops throughout a circuit. And then we have the current rule, also known as the junction rule, which relates currents. So first, energy conservation is encoded in a circuit using something known as Kirchhoff's voltage rule, which says if you walk all the way around a closed loop, usually a full circuit, then the voltage drops must sum to zero. So this is actually a consequence of conservation of energy. And all this says is that any height you gain by being stepped up in the battery must be eventually dropped as you make your way around the loop. Which should make sense, because as we've looked at all of our circuits so far, they've obeyed this loop rule because you start at a height of zero, you get elevated to some potential, and then you're back to zero by the time you make it around. If not, you'd have some sort of runaway energy where you could gain energy around each loop and it would create an infinite energy glitch, so to speak. So we're going to agree to write loop equations as follows. The sign of delta V is determined by the direction you're traveling in the loop relative to current. So if you go through a battery from minus to plus, which is usually how we go, that's going to be a positive delta V because you're gaining height. But if you travel through a resistor in the direction of current, that's going to be a drop in voltage. And if for some reason you go against the current that through a resistor, that would be a gain. That shows up in very rare cases with multiple batteries. So we've already analyzed series circuits before, but we're going to show that you actually don't need to know REQ to solve a series circuit if you know this idea of the loop rule. So we have a series circuit, and again, we really love this idea of color coding electric potential to get an idea of what's going on. So remember, the potential explores all possible paths until it hits a circuit obstruction, and we get a third color in this circuit because we have a closed loop and we ran out of colors. So recall that we have the freedom to choose our zero height at whatever point we wish, so we always pick zero potential to be the negative terminal of the battery. And if this battery steps us up by 6 volts, that means our high potential would be 6 volts. So we're just missing this sort of mystery potential that could be anything between 0 and 6. And Kirchhoff's loop rule is actually why we know for sure that no matter how we make it around the loop, we got to go from red to blue. We got to somehow drop all of these 6 volts somewhere. Now, how it's done depends on the resistances. So what is a loop equation for this circuit? So loop equation is defined as saying the sum of all the voltage changes must be 0. So let's think about it. So usually we say we start at this negative terminal of the battery and we make a literal loop around the circuit. So let's see what we would do. So first, we would encounter the battery, and that would be a gain because we're traveling uphill. So first, we would travel uphill across the battery terminals. Then we encounter our first object. We would encounter the 4 ohm resistor. And we know that we're going to drop some volts across the resistor. So we know that we are going to drop some volts across the 4 ohm resistor. Then we would encounter the 8 ohm resistor, and we're going to drop some volts across that. But oh look, after I've gone through both resistors, I'm back to the blue color. I'm back to the bottom of my circuit, so that means my loop is complete. So if we actually look at this equation, it should make sense, because all we're saying is that we step up our potential from the battery, and then we drop potential in 2 places around that loop. Now, this isn't entirely a loop equation because we have not written this out in terms of currents is usually what we want. This is valid, but we want to usually substitute. So notice that this is a series circuit, and in series, the current through the circuit is the same. So everybody is going to receive the same current I. So this means that we can write a loop equation as saying the battery voltage, which was 6 volts, minus the voltage drop through the 4 ohm resistor, which is going to be I times R, which is 4, minus the voltage drop through the 8 ohm resistor, which would be I times 8, gets us back to 0. So I would say that if we're just looking at writing a loop equation, maybe we'll box this one because we haven't substituted anything in. We'll say we'll box this as the loop equation, and to actually solve it, we'll start substituting. So again, we know that this was our battery EMF, this was IR for the first resistor, this was IR for the second resistor. So we see something interesting happens, because now we could get 6 is equal to I times the quantity 4 plus 8, because I have a 4I and an 8I. And I wrote it weird this way so you could see, oh look, it's REQ. So what is I? Well, I is just going to be 6 over 12, which is equal to 0.5 amps. So this is actually not too far off how you actually derive REQ for a series circuit, how we prove the formula. Because notice around this closed loop, we see that since the I is the same, you can factor the current out, and we just end up summing these resistances. So this is how you'd solve a series circuit using what's known as the loop rule, or writing a loop equation. So why is that helpful? Well, of course, we said unlocking the total current in series is helpful, because now it's not just I, it's 0.5 amps. So calculate the voltage drop across each resistor and label each value. So delta V across the 4 ohm is just going to be IR of the 4 ohm, which is just 0.5 amps, times our 4 ohms, which is 2 volts. So that is our first voltage drop. And then, of course, we can just do some shameless copy pasting for the 8 ohm resistor. Same process. 8, 8, 8, and you become 4 volts. So now's our opportunity to check that we did this correctly, because the current is the same. So now we can look at our voltage drops. We are dropping 2 volts across the 4 ohm, and we're dropping 4 volts across the 8 ohm. And look at that. Our drops are 2 and 4. And if we add our drops of 2 and 4, we get to 6. So this means our little intermediate potential here is 4 volts. And you know your loop rule works if you can get these intermediate potentials forwards and backwards. So if you go forwards, I would say 6 volts, drop 2 gets me to 4. If I went backwards, I would say 0 volts, gain 4, also gets me to 4. So it works. Great. So these loop rule equations are consistent with our normal analysis. And notice we see the other things we expect. Like if this was our wait times at different stoplights on a 1-lane road, cars would be spending more time at the stoplight that takes more time. So here's an interesting representation called the loop rule diagram. On the axes below, sketch the value of the electric potential around the loop, defining the negative terminal of the battery as 0 potential. Well, it seems pretty natural that we should be counting by 2s here, because the maximum potential in our circuit was 6 volts, and all our drops are going to be multiples of 2. So this is what a loop rule diagram looks like. So we start at low potential. Then trying to think what. Yeah, we'll use the line tool for some of these. Then our battery steps us up to 6 volts. So the battery steps us up to 6 volts. No potential change throughout wires. But then we approach our first resistor. So notice if we go back to our first resistor, it says the voltage drop is 2 volts. So we are going to drop 2 volts across this first resistance. No voltage drop through wires, and then we drop 4 volts across R2. So notice this is going to be consistent with what we found, because this voltage drop goes from 6 to 4, which is 2 volts, and this voltage drop goes from 4 to 0, which is 4 volts. So this is known as a loop rule diagram. It's sort of this roller coaster. It's sort of this roller coaster looking representation where we see that the battery steps us up from 0 to some maximum value of the potential, and then we drop that potential throughout the loop. And for any valid loop rule diagram, it needs to close in on itself. All right, indicate which resistor is dissipating energy at a higher rate. Justify your answer by referencing your potential graph. Well, first of all, we know the current is the same through these resistors because we're in series. And we also know that power is I delta V. So we can see that the resistor that will be dissipating more power is going to be the one with the larger delta V because I is the same. So it's going to be R2 because notice R2 has a larger jump across it, a larger voltage drop. R2 is dissipating power at a higher rate. Both resistors are in series. They receive the same current, so the voltage drop across R2 is higher, meaning more power is dissipated. And then we'll quickly verify why this implies total energy is conserved around the loop. So this is an input-output situation. So notice that around the loop, there's no net change in potential. So this means there's no net change in potential energy around the loop. So energy is conserved. And you can relate this to the mechanics idea of a conservative force. No net work is done on a closed loop if you have a conservative force. Same idea here. So the loop idea being closed and there's no net energy change, that is how we are encoding energy conservation. So that's known as the loop rule. A consequence of the loop rule involves what we call real batteries. So we have been pretending that our batteries do not have internal resistance. And this is our ideal battery, where if you just connect the battery to the resistor and you measure your voltage across the battery, its EMF doesn't change no matter what you connect it to. Because loop rule says, well, if the battery EMF is epsilon, you must also drive epsilon across the resistor. They exactly match. But for real batteries, we're modeling real batteries as a battery with a resistor in it. So when we talk about a real battery is really a little mini series of a battery and a tiny internal resistance inside. So what does this effectively mean? Well, this means that, yeah, it's true that if there was no current in your circuit, the battery voltage would still be epsilon. But now, if you have resistance inside your battery, and again, this is not a physical resistor, this is the resistance inside the battery that you just can't remove, there's going to be a drop inside the battery. So what this means is your battery's voltage is effectively lowered in the non-ideal case. Because, yes, its original EMF is epsilon, but you're losing some of that because there's a drop happening inside the battery that you can't get rid of. So the more and more current you're going to be pumping through your circuit, the more and more drop you get inside the battery itself. So we call this delta V terminal. This is the terminal voltage. This would be the effective voltage of your battery. So this is not an issue if there's no resistance in your circuit, in your battery rather, but this is an issue if there is internal resistance, because you're going to lose some of your battery's effective EMF due to the internal drop. And we can set up a loop equation to actually model that. So this is a classic lab that works pretty well. A group of students are investigating a battery with unknown EMF, epsilon, and internal resistance little r. They attach the battery to a variable resistor and wire in multimeters to measure the total current I in the circuit, as well as the terminal voltage of the battery. Now, why these students don't just probe the battery with nothing attached to get the EMF is beyond me. I know I wrote this, so I made it contrived because you'll see something cool with the best fit line. So first we're just gonna draw this with standard notation and then derive an expression for the effective battery voltage. So if we draw this circuit, we have a non-ideal battery. So we're gonna model the non-ideal battery as sort of its own object right here. And there's some variable resistance that we actually don't know. And we also don't actually care about it in this circuit. And we're also given that we've put some multimeters into this circuit. So we're measuring the current. I'm actually gonna, now we'll keep the resistance. So current goes in series, right? Because current is the same in series. So that's why my ammeter is connected in series. And then to actually measure my battery voltage, of course, we can't see that there's a little resistor in here. But effectively, what we're doing is we're just probing both ends of the battery, and it measures what we've been calling the terminal voltage. So we want to derive an expression for this delta V across the battery. So notice that what is delta V terminal? Well, delta V terminal is the effective voltage of our battery. So what this means is that it's the isolated EMF. This would be if there's no losses inside, but we can see it's not going to be equal to epsilon because we're going to be losing some of our effective EMF due to the internal drop. So it's going to be epsilon minus the internal drop. So what is the internal drop? Well, we actually measured our circuit to have current I, and our internal resistance is R. So that's actually it. So our equation is the terminal voltage of a battery is equal to the EMF with no current minus the IR that's dropped inside. So that should make sense because our current in the circuit is I, so we're going to drop IR inside the battery itself. So that goes to lower the effective voltage. So notice what happens here. So as the students pump more and more current through the circuit, the effective battery voltage keeps decreasing. Because if you pump more current through your circuit, the internal dropping is going to be larger. Because if you have a larger current, you're going to drop more volts inside the battery versus outside. So we can see the battery is effectively getting weaker as you pump more and more current through because you're losing some of your voltage drop to the internal resistance. So our equation, we're trying to get the internal resistance of the battery, which is usually the objective of this lab. Should help that our variables were the terminal voltage and the current. Everything else is a constant. So we can do some rearranging. So notice I can rewrite this as negative R times I plus epsilon. So this is a really interesting linearization because we get some things that aren't common in this class. So first, we actually didn't need to transform anything. You totally could. Some of these things might actually bother you, and you might want to graph something else. But actually notice we get a couple things with this linearization that aren't particularly common. So remember that we can write this as y equals mx plus b. So what this tells us is actually we have a slope of negative internal resistance. So the internal resistance would be the opposite sign of the slope. And then look at this. We have a plus b. That's not the most common thing in the world. So we actually get a real physical y-intercept, and it's the EMF of the battery. And that should make sense. Because if you have no current in your circuit, you can't lose any voltage. You can't lose a drop. You can't have any dropping inside the battery, so the battery is at full strength. So we can just graph the terminal voltage on the y versus the applied current on the x. So we can actually solve for two quantities here. So that's why I said the EMF is unknown, because I can make you solve for it. All right. As per usual, here's a more, this is one of the more scuffed off-camera mining expeditions I went on, because we have a giant broken graph here, which pretty sure that's legal. Don't quote me on it, though. It is a linear scale. I just showed it was broken. So current, amps, scaled my axes, linear scale, voltage in volts, linear scale, drew my points. Pretty decent best fit line, though. So notice a few things. We get a negative slope. That's what we thought. And we get a non-zero y-intercept. So here's our Desmos equation when I ran it through the regression. So this is a really easy calculation to do because we actually were just given that slope was equal to negative of the internal resistance. So the internal resistance is just the negative of negative 0.65, so 0.65 ohms. And it makes sense that this is a rather small quantity. Usually we're assuming our batteries to be ideal, so we should not expect the ohms inside our battery to be very large. And then calculate the battery EMF. Well, we also have a nice relationship that says the y-intercept of our graph was equal to the battery EMF, and that's 9.05 volts. And notice this should make sense. This should make sense if we look at our graph. 9.05. That looks pretty consistent. I would definitely believe that. Yeah, it looks definitely in the middle of 9 and 9.1. So that's kind of everything we can do with the loop rule before getting into complex circuits. So now we have an easier rule to understand, which is called the junction rule. And this is just conservation of charge. So if you have a junction, meaning a point where there's multiple paths, so this is about parallel circuits, the total current into the junction has to equal the total current out of the junction. So if you have a 2-lane drive-through, the number of customers that entered the drive-through must be equal to the sum of the customers at each lane. If lane 1 served 3 people and lane 2 served 4 people, there must be 7 people that entered. This says that charge can't vanish. This is very similar to the continuity equation for fluids, where when your water reaches a junction or the pipes split, the water doesn't equally split between the pipes if the diameters are different, but they will split, and the total amount of water per second flowing has to be the same. The junction rule tells you nothing about how it splits, though. We know that in a parallel circuit, the larger resistances get lower currents, using our fast lane, slow lane analogy, but the junction rule doesn't tell us that. All the junction rule says is that the branch currents must sum to the total. So here's a rather contrived example where we want to set up a junction equation. So we have 5 currents here. So what the junction rule says is that the sum of the currents in to the junction must equal to the sum of the currents out. So maybe let's label these as in or out. Well, again, a junction, this would be the sort of junction point. It's where paths meet and branch off. So I1, you're going to be an in. I1 is heading into the junction. I2 is heading into the junction. And then it looks like the other three currents are heading out. I3 is heading out, I4 is heading out, and I5 is heading out. Because we see that I1 and I2 point towards the junction, I3, 4, and 5 point away. So what are our currents in? I1 and I2. What are our currents out? I3, I4, and I5. That's all there is to it. Notice this does not help us solve for relative amounts of the current. This just sets up a conservation equation. You need to throw in some loop rules to actually get these individual currents. So let's use the junction rule in a parallel circuit now. All right, you know what we're going to do. I see a circuit, so I am going to draw myself a color-coded potential diagram. Oh, this is interesting. I've reached an ammeter. So does the color pass the ammeter or does it change? Well, we assume our current meters are ideal, meaning there's no resistance, so there should be no drop across this ammeter. So we actually assume that there will be no potential drop across the meter. And this is a 12-volt battery, so we step up our low potential of 0 volts by 12 to get to 12 volts. So that allows us to pretty easily see that our delta V across each of these resistors must be 12 volts. This is our 2-lane drive-through. You can go through the fast lane, which takes 3 minutes to serve you, or the slow lane, which takes 6 minutes. Each drive-through lane is open for 12 minutes. We want to find the customers that get served in each lane. All right, so first we're going to draw some loop diagrams. First, we're going to use the loop containing the battery and the 6 ohm resistor only. That's the wrong one. Okay. Battery and the 6 ohm resistor. So we're going to just say this is 12 volts, our highest potential. So what's going to happen here? Well, that would be this loop right here. So we see that if we go through our journey, we would get stepped up by the battery, then we'd drop our height through that 6 ohm resistor. So we would get this as our loop diagram. See that we get stepped up across the battery, and then all the voltage of the battery is dropped across the 6 ohm because it's the only thing in the loop. And there's literally no change for the 12 ohm. Interesting. We will say this is the 3 ohm resistor. I don't know where that came from. This is the 3 ohm resistor. We'll have to send that to the editor, which is me, by the way. So we get the same exact loop diagram here. Get the same loop diagram because regardless of which of the two paths we picked, notice that you just walk through the battery and a single resistor before coming back. I think the voltage was stuck in my head somewhere. So I must have just said 12. So we're going to calculate this reading on the ammeter 2 different ways. So first, we're going to find the individual currents and apply the junction rule. So why should that work? Well, this is my total current that's being observed. Because if we actually look at it, we can say that there's sort of these 2 junctions, and we would get the same result either way. So notice that going out of this junction this way, there's I through the 6 ohm, And going this way, it's going to be I going through the 3 ohm. And this would therefore be I total. So we see the total current, or the total amount of customers, enter the drive-through, and they pick which of the 2 lanes to go through. So we know that the total customers must somehow split between the 3 and the 6. Now, we would get an equivalent junction equation if we go over here, sort of after they're served, because we'd see that this is I from the 6 ohm going in. This is I from the 3 ohm going in. And then we get I total going out. So either way, we'd get the same sort of junction equation because we see that the 3 ohm and the 6 ohm currents must add to the total. So our first claim is that we can just find these 2 currents individually and add them to get the total that goes through the ammeter. So we know that current is equal to delta V divided by R. And we also know that delta V is the same in parallel. This is just a fact. And actually, it's not just the same in this circuit, it's equal to the battery voltage. Our potential diagram should have shown that pretty easily, that this is going to be 12 volts across each. So, I through the 6 ohm is equal to delta V of the battery, which is 12 volts, divided by 6 ohms, which is 2 amps. I through the 3 ohms is the 12 volts dropped across the resistor, divided by 3 ohms, which is 4 amps. So the reading on the ammeter is the total current. So I total is just going to be 2 amps plus 4 amps, which is equal to 6 amps. So this is telling us that 2 customers got served in the slow lane, 4 got served in the fast lane, so 6 customers got served in total. What about the equivalent resistance of the circuit? So there's also another way to find total current, because we also said that I total can always be found by taking the battery EMF and dividing by REQ. So what is that? Well, this is a parallel circuit, right? If we go back up, it's a 3 and a 6 in parallel. And this is one of my favorite math facts that I use in this class all the time, because it's the simplest parallel that works out. That's non-trivial at least. And that's 3 plus 6 equals 2. So what do we mean by that? Well, REQ is going to be equal to 1/3 plus 1/6 to the -1, because we're combining them in parallel. So when I say 3 plus 6 equals 2, I mean in the land of the reciprocal rule. Because we said that, of course, please just type this in your calculator. I literally messed this up when I did this last video. I found it, but still. The shortcut says you do product over sum. So this is 18 over 9, which is 2 ohms. So 3 plus 6 equals 2, as long as you're talking about parallel resistances. So battery voltage is still 12 volts. REQ is 2 ohms. So we get 6 amps. As expected. There we go. We got to use as expected today. Got our 6 amps that way. So usually in parallel circuits, I total is less useful because it's the individual currents that are usually what we want, but it's always a nice consistency check. Lastly, we're just going to outline a couple experiments you could do to verify Kirchhoff's rules. So describe a procedure to verify Kirchhoff's voltage rule for a circuit containing 2 resistors in series. We have access to an ideal battery, so we can ignore that internal dropping, and 2 different resistors and a multimeter. Multimeter means it can do whatever you want it to. So Kirchhoff's voltage rule, 2 resistors in series. So if we have 2 resistors in series, we know that we're just making this circuit. So what does Kirchhoff's voltage rule say? Also known as the loop rule. Well, the loop rule says stuff about voltages. So you can imagine that if we're verifying the loop rule, we're going to want to determine all these voltages. So you can probe these one at a time. So first, you would take the voltage across the battery terminals to get the battery voltage. Then you would probe across one resistor. Then you would probe across the other resistor. And loop rule says it should add up. So what does the loop rule say? Well, the loop rule says the sum of the delta V's must be equal to 0. So what are you doing? You're checking. You want to check that the voltage across the battery minus delta V across the first resistor minus delta V across the second resistor must work out to 0. Because you gain some potential that is stepped up by going through the battery terminals, and then you drop it across both resistors combined. So if your two voltage drops sum to the battery voltage, the loop rule holds. That's what you're looking for, because you're looking for the two drops to equal the gain. Because again, you're saying that you're going to gain potential by stepping across the battery terminals, and then you drop it in these two places, so the two drops must equal the gain. No net change on loop. And if it doesn't, it's almost certainly going to be off by undercounting the drops, because there's going to be some internal resistance in this battery that we haven't accounted for. So the missing voltage drop will be your internal drop. All right, and then we have its sibling. Verify the current rule for the circuit containing two resistors in parallel. So to make it more clear what we're going to do here, I'm going to draw the parallel circuit in more lines than I typically would. So again, this is a parallel circuit, and Kirchhoff's current rule is also called the junction rule, which means that the current in is equal to the current out in our circuit. So how can we do that? Well, here, when we did the loop rule, we were checking voltages and seeing if that rule held. So we're going to be doing the same thing with current. And remember, current is in series. So I could measure I could put a current meter right here, and this would measure, we'll say A1. I could put a current meter here, and this will measure A2. And I could put a current meter here, and this will measure A3. Because if we have our total current in the circuit, this would be our current I1, and then our current would split into I2 and I3. To avoid clutter, I'll put these underneath. So we're just checking that the current in I1 should be equal to I2 plus I3. So what would it mean? What would it mean for this junction rule to be satisfied? Well, we're just checking that the reading on these meters work out. So check. So if the readings on the meters work out, where the total current meter reading is equal to the sum of the readings on the branch current meters, the junction rule is satisfied. We actually do this one. We do this one in the lab, and I get pretty consistent student results with this. Like, we'll get it correct to about like 100th of an amp. We'll see that this will work out. And any differences are usually due to the fact that we're moving these ammeters around and there's some internal resistance in there that we're not accounting for. But this is a pretty simple verification of Kirchhoff's junction rule. So we see that for the junction rule, you're checking if the branch currents sum to the total current, and for the voltage rule, you're checking if the voltage drops is equal to the voltage gain from the battery. So that's Kirchhoff's rules. So that just leaves analyzing circuits that aren't purely series or parallel.